Hi guys, welcome to this new tutorial and let's make this proof of work. So, first of all, what is exactly a proof of work? A proof of work is the number or piece of data that the miners have to find in order to mine a new block. So we're going to define a problem and the miners will need to solve that problem, and to solve this problem they will have to find a specific number that will be exactly this proof of work, and that will be this proof argument expected by the createBlock function. So we'll define a problem that will be challenging to solve but easy to verify. And that's the principle, that's the key point to understand about the proof of work. It's a number that is hard to find but easy to verify. Why does it have to be hard to find? That's because if it was easy to find, well, miners could easily mine tons of blocks. And for example, if your blockchain holds a cryptocurrency, well, the miners could easily get tons and tons of cryptocurrencies. And therefore, since it is easy to get, it has less value. So we have to make it hard to get for it not to lose its value. And why does it have to be easy to verify? That's because when a miner solves the problem and finds a potential proof of work, well, the other miners need to verify that indeed the first miner solved the problem. And so that's exactly what we'll implement in this proof of work function. This is a function that is not only going to define the problem to solve, but also that will solve this problem. And that's why at the end of the function, we will return the proof of work, which is this proof expected by the createBlock function. So let's do this. Let's define this function. So we start with def. We give a name to this function, which I choose to be proof of work. And this function is going to take two arguments. The first one is self, of course, because we will apply this proof of work method from the instance object that will be created from the class. But then there is another argument, which is the previous proof, because in order to make that problem that the miners will have to solve, we'll take into account the previous proof. So in other words, the previous proof is an element of the problem that the miners will need to consider to find the new proof. No worries, it's going to get much more clear once we define the problem. So let's input the previous proof here, previous proof, and there we go, let's define this function. Alright, so what do we need to start with? Well, we're going to start by introducing the new proof variable that we initialize to 1. Why do we initialize it to 1? That's because to solve the problem, we're going to increment this new proof variable by 1 at each iteration of a while loop until we get the right proof. So basically, we're solving the problem with the trial and error approach. Okay? So new proof starting at 1. Then, just before we start this while loop to increment this new proof and check if it is the right proof, well, we need to introduce a new variable that will check, indeed, if this new proof is the right proof. And so this new variable, we're going to call it check proof, which will initialize to false, of course, because so far this new proof is not the solution to the problem. All right, so check proof equals false, and then once we find the proof that is the solution of the problem, we'll set this check proof variable to true, and that's when the while loop will stop. Okay? And speaking of the while loop, that's exactly what we're going to start now, starting this while loop. So to make a while loop in Python, we need to start with while, and then, so according to you, what is the condition of this while loop? Well, as we just said, we want to iterate in this loop by incrementing new proof by 1 at each iteration until we find the proof, and therefore until check proof becomes true. That is, while check proof is false. And therefore the condition here will be while check proof is false. While check proof is false, we will iterate try, fail, then increment new proof, try again, fail, then increment new proof, until we find the new proof that will solve the problem. And speaking of the problem, that's exactly what we're about to define right now. As the first step of this while loop, we will define in 2 lines the problem that the miners will have to solve. So, what is this problem going to be? Well, we're going to use, of course, the hash function. We're going to use the SHA-256 cryptographic hash function combined to the hex digest function to return a string of 64 characters, and this string will need to start with what we call 4 leading zeros. The leading zeros ID is a classic way of defining a problem that the miners have to solve to find the proof of work. And the key thing to understand here is that the more leading zeros you impose, the harder it will be for the miners to solve the problem. So we're not going to demand too many leading zeros because I want you to mine the blocks very easily. We're not making a real cryptocurrency that will be traded all around the world today. It's just for educational purposes. So we'll make a simple proof of work with 4 leading zeros. And we're going to start by introducing a new variable that I'm going to call hash operation. And this will be this string of 64 characters, but we call it a string of double length containing only hexadecimal digits, meaning digits going from 0 to 9 and A, B, C, D, E, F. That's just the hexadecimal arithmetic format. You can check it on Wikipedia. So this is what we want to return now, but inside this SHA-256 function that will return this kind of string, we will define this operation here, which will be an operation taking the previous proof and the new proof. So this operation can be anything, but you're going to see it will only need to be non-symmetrical. And I'll explain why in a few seconds. So let's make this hash operation. And so now we're going to take the hashlib library. From this hashlib library that, by the way, we import here, well, we're going to take the SHA-256 cryptographic hash function. So it's a function, so I'm adding some parentheses here. And that's where we input the operation of the previous proof and the new proof. So what is this operation going to be? Well, as I said, it has to be non-symmetrical. So for example, we cannot take new proof plus previous proof, because new proof plus previous proof equals previous proof plus new proof. And therefore, since we increment new proof, well, at some point, the new proof will become an old previous proof. You will be able to check that when mining the blocks. You will see that you will have the same proof every 2 blocks, and that's only because the operation is symmetrical. So in order to make that operation non-symmetrical, we can simply take, for example, the operation new proof minus previous proof, because new proof minus previous proof is not equal to previous proof minus new proof. And therefore that works. But this is much too simple. We're going to make that slightly more challenging, but not too challenging. So I'm just going to add the square here and also the square here, so that we take the square of the new proof minus the square of the previous proof. And that's already better, but still, this is very easy. You can practice to make an even more complex operation to make the problem even more challenging. All right, and now to make this acceptable, we simply need to add some code that will give us the right format that is expected by this SHA-256 function. So first, we need to input this, that is the square of the new proof minus the square of the previous proof, into a string. So I'm putting all this into the string function. And then that's not all, we need to add here .encode, the encode function, which will encode the string in the right format that is expected by this SHA-256 function. So what this encode function will do exactly is add, you can check in the console, a b before the string. So for example, if the square of the new proof minus the square of the previous proof is equal to 5, well, string of 5 will be 5 in quotes, and string of 5.encode will be b quote 5 quote. All right, you can check that in the console. That's just for format purposes, so that SHA-256 accepts this operation. All right, so encode, and then as I said, we're working with the hexadecimal format to get this string of double size containing only hexadecimal digits. And to get this, we simply need to add here .hexdigest. And it's a function, so we add some parentheses. And taking back our previous example, here is what we get. All right, so that's our hash operation. And so now what we're going to do is define the second part of the problem, meaning we're going to check if the first 4 characters of this hash operation are 4 zeros. That's the 4 leading zeros I've been talking about. And if these first 4 characters are 4 zeros, well, we win, well, the miner wins, and check proof will be set to true, and the new proof will be returned. That is, this new proof giving us the result of a cryptographic hash starting with 4 zeros will be the proof accepted to mine a new block. All right, so let's do this. Let's make this condition. So if, because we need to check something now, if our hash operation starts with 4 zeros, and therefore we're gonna add some square brackets here and take the first 4 indexes of this hash operation, which is a string of 64 characters. So we're going to take the first 4 strings, therefore taking the first 4 indexes. And to take the first 4 indexes, we need to take the range from 0, because indexes in Python start at 0, up to 4. Be careful, because the upper bound of the range in Python is excluded, and therefore here we take the indexes 0, 1, 2, and 3. And that's exactly what we want. So if the first 4 characters of our hash operation are equal to 4 zeros that we have to put in a string, because of course our hash operation is a string, well, in that case the miner wins and check proof is set equal to true. And that's it. But if the miner loses, if the miner cannot find this new proof at the specific stage of the while loop, that is at the specific iteration of the while loop, well, in that case, else, colon, he loses, and therefore check proof is kept to false. Check proof is kept to false, but we give another chance to the miner. He will increment, well, his algorithm will increment the new proof by 1 to test if this new value of the new proof incremented by 1 will give this whole operation here encoded and hashed into the X-Digest format a string that starts with 4 leading zeros. All right, so that's why what we have to do now is increment new proof by 1 to try with the next value. Okay, and finally, now that we did both cases, well, as soon as we find the hash operation starting with 4 leading zeros, that is as soon as check proof equals true, well, as per the condition in the while loop, we stop the while loop and we return the new proof. We return the new proof that will be exactly the proof expected by this createBlock function, which I remind will be used right after a block is mined. All right, so we end this function by returning the new proof, and congratulations, you have made the proof of work function.